Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to graph two special plane curves. One is called Prolate Cycloid, and the second one is called the Folium of Descartes. Again, these are two special plane curves of calculus. And let me just give you some hints about the graphs of these functions. Um, in the first one, you have the prolate cycloid. As you see, it's a very periodic curve, and it follows a specific direction and specific form. And in the second case, we have the folium of Descartes, and that also follows a very specific trajectory, as you see. In both cases, we're going to be able to use our calculator to graph these functions. And as well, I'm going to have like a table of sample values just to verify my findings in the graphic calculator. All right, so I'm going to go into details in the video of graphing these two special plane curves, and let's get started. All right, let's start with part A. We have the parametric equations provided for the prolate cycloid. And we don't know what that is at this moment, but we're following the strategy that we developed earlier, that we're going to have like a table of sample values for, in this case, theta. Theta is the parameter, right? So that we will have enough number of sample points for theta to get the xy coordinates in the xy plane. Okay, so let me just show you what I got, and then please have your TI-84 ready, and please set it to the radian mode, and let's start. Here we go. I have chosen t's going from negative 2 pi to 2 pi. In fact, sine and cosine are 2 pi periodic functions, so minus 2 pi to 0 or 0 to 2 pi with smaller increments would also work for me to construct this curve because one loop takes like 2 pi for the t values. But I want to get like maybe 2 loops out of this to, in fact, this two of the same of those curves. So let's start with t equals negative 2 pi, but again, your choices could be totally different, and the increments that I gave here is pi over 2 from one to another. So you may reduce that down to pi over 4 if you want to. Okay, so for negative 2 pi, we have, once you plug negative 2 pi back into x and y for t, so you get negative 12.57 and negative 2. That's me right at this point here. This is my starting point, okay? So my next point is going to be negative 13.42 and 2. There we go. I'm going in this direction, okay? And without you putting the blue curve down there to connect those dots, please first, in your version, in your side, just put the dots only, and you can just join those dots by the continuous curve at the end, okay? All right, so at negative pi, we have negative 6.283 and 6, and we're somewhere right here, okay? We're still going in that direction. We're still following that trajectory. And at negative pi over 2, we have 0.8, 0.85, and 2. Here we go. I am right here. Okay, we're still following that direction. And now let's see what we have at 0 for t. We have 0 and negative 2, so we're making a turn all the way, and we're just right here. Okay, good. And then this looks to be one loop, in fact, right? Because I have the interval negative 2 pi and 0, which has the length 2 pi. That tells me exactly what the one loop looks like, okay? So if you just keep going in this direction, guess what's going to happen? Well, we're going to copy paste, right? Because we're going to sort of like get the same type of pattern starting from this point all the way down here. So this is the second period, okay? And as you see that as the time moves, let's call the t parameter time, as the time moves, I'm going to get another copy-paste situation going on between, for the interval 2 pi and 4 pi. and 4 pi and 6 pi I have another one. So this keeps looping like this, and this is called a Prolate Cycloid. Okay, so this is a very special trajectory. It's used in many applications. So it's good to know what a Prolate Cycloid is at this moment, okay, for you. And how about the second one? Because we're done with graphing with the Prolate Cycloid. So we have the Folium of Descartes, okay? So it's x equals 3t divided by 1 plus t cubed, and y equals 3t squared divided by 1 plus t cubed, okay? So so we don't have any cosine or sine. We don't know if this is periodic. In fact, it shouldn't be. It shouldn't be periodic. Okay, so let's see what kind of graph we get for my sample choices of t, and yours could be totally different from that. All right, here we go. So I chose my t values starting from -2 going all the way to 2.8, but this could be totally different for your case. You can start with t equals 0 going all the way to 4. Just put enough number of points so that you can actually see the full picture here. Okay, so let's see what's going on. For t equals -2, I have 0.85 for x and -1.71 for y. Okay, where is that point located? Right here. This is my starting point based on what I picked for t, okay, initially. So the next point is -1.4. It is 2.40 for x and then -3.37 for y. Here we go. I'm right here, so apparently I'm going in this direction. Okay. Interestingly, the next t takes you completely out of fourth quadrant. Okay. So because you get something like -4.91 for x and plus 3.93 for y. So you're not in the fourth quadrant anymore, but I'm right here. I jumped back right here. So that's pretty interesting. Okay. And for t equals -0.2, I have -0.60 and 0.12 for y. Here we go. I'm right here. So for some reason, I'm going in this direction. I was going in this direction, but all of a sudden, I jumped to the second quadrant. Now I'm following this direction. Okay. So let's see what's going on for 0.4 and 1. I have 1.5. 1.5 for t equals 1, and 1.12 and 0.45 for t equals 0.4. So these are the points here. So apparently I'm going in this direction, and if you keep going, okay, you hit those points, and eventually I track back where I started. Okay, so I'm back to the trajectory I started with. Okay. So you can see like this kind of like weirdness going on in graphing parametric equations. So just that's why I said like you should keep enough number of points. For example, if I started right here and maybe if I was going in this direction for different choices of t, I wasn't able to see that the graph was making this kind of like inner loop in between. Okay, I wasn't able to see that. So to be able to see that inner loop with this parameterization, you have to put t's in between, let's say -0.2 and 1.6, so that you would be able to see that loop happening on this trajectory. So and this happens a lot in sending rockets to the space, because to get into the orbits, you have to make sharp turns sometimes, or make loops to get into the orbit of different planets. Okay, so again, to be able to see that behavior, you have to have good chosen t values so that you can have that inner loop presented in your graph. Okay, so make sure to sometimes get the range of t values to be large enough so that you won't miss any kind of like weirdness going on here. Okay, all right. This takes care of part B, and I think that makes the end of the video. All right, so if you have any questions or comments, please send those to my way, and I'll see you in another video. Bye.